else know? Ngoy?
Ngoy?
Thank you.
Yeah.
In Cantonese.
I don't know.
You don't know Ngoy?
No.
I know it. See, I know more Cantonese than you.
Yeah, but I know more Chinese than you.
Probably. What?
She.
Wuhan is my city accent. My city.
Yeah. City accent.
Very
Different from the
She has a city accent.
Yeah.
I see.
Different city
She has
accent.
a Dublin Chinese accent. I understand.
special.
Very special, yes. Okay. Right, so this is your last topic in engineering maths. So last time with Joan you did the bell curve, yes? You remember doing that? And the probability tables? Normal distribution, yes. Okay, so to get started, let me just so we'll do something. Oh no, be strong, Grace, be strong. We'll motivate this with an example from like with physics, since you're all engineering students. So, for example, maybe you want to measure something like G. So, of course, we have 5 people here. So, we'll have A, B, C, D, and E. So, each person, they do the experiment many times, and they get a value for G. So, maybe Grace gets 9.8, and then Sohi, maybe she gets 9.9, and then Hareen, he wasn't concentrating, so he gets 11, and then here we'll get a 9.5, and then Amanda, that's Andy, and then Amanda
100.
okay, 10 then. This is Grace, Sophie.
No, and
The numbers, yeah. This is calculating G from the experiment. Remember with the pendulum?
Oh.
Yeah. So how many times did you do the experiment? It was 10 times, wasn't it?
Yeah.
So this is 10, and this is 10, and 10, and 10, and 10. So this number here, this is the average. The average, yeah? You can get this from the graph if you want. But you remember in your calculation, you have to calculate the uncertainty. So for example, maybe this answer is 9.8 plus or minus 0.1. Yes? Or maybe this one here is 9.9 plus or minus 0.1. And so on. But what we would like to do is maybe put all of these together and take the average. Okay? So this is the reason why we're interested in this. I'll give you another example, maybe a little bit easier to picture. So last time you did the bell curve, the normal distribution. So let's imagine you have a tree and it grows here. And the tree can have many different heights. So it has an average, and then it has a standard deviation. So the first person they measure and they get x1 and then sigma 1. Then maybe another person comes along to a different part of the forest and they measure and they get an x2 and they get a sigma 2. So what I'm trying to say here is that the trees, their heights will be on a bell curve. And here also the trees, their height will be on a bell curve. What we're going to do today is combine. We're going to put this one together with this one. We want to know how does the average behave. So I'll just do one more to try and help you really understand. Again, maybe with the trees. So there's my tree, beautiful. So here's the height of the tree. So maybe the average height is 160 centimeters. Do you understand? Like that's that. But let's say we have many trees and we add up all their heights and we divide by how many we have. What should the average be here? It should still be 160, but there's a difference between the standard deviation. In this picture, the standard deviation is how much the tree's height can change. But in this picture, what does the standard deviation represent? Does anyone know?
How many types of trees?
Not quite that, no. Not quite. This one here.
How many trees are there?
Oh, I just 160
160.
centimeters. You know what? Let me show you what.
And deviation is the tallest tree minus the shortest tree, right?
Not quite. Well, it's getting a bit complicated. I want to show you with numbers, okay? So I think the numbers will help. Okay, so here's the first. So here's Amanda, Sophie, Irene, Andy. What am I doing? Grace, Sophie, Irene, Andy, Amanda. Is that everybody? Yes. So Grace goes outside and she measures the heights of the trees. So I don't know, she'll get heights like 1.5, 1.6, 1.2, 1.9, 1.8, something like that. Okay? So she has an average. Yes? And she also has a standard deviation. So there's her average and standard deviation. Okay. Now Sophie goes out and she goes to the forest as well and she measures some trees. So she can be 1.4, 1.5, 1.3, 1.8, 1.7, for example. And she also measures and she gets an average. Now, why is her average not the same as Grace's? She measured different trees, but they should be about the same, right? They should be nearly the same. So Hareen, let's say 1.55, 2, 1.7, 1.8, 1.6, and kind of. Oh, okay, all right. He went to the wrong part of the forest, maybe. Right, 1.5, 1.6, 1.9, 1.8, 1.3, and then lastly we'll say 1.6, 1.6, 2, 2, 1.4. So we get this here. So can you see that everybody has about the same average height, and everybody has about the same standard deviation? But if I add these four together to make a total, the average here will be, for these four, 1.62, and the standard deviation will be for these four. Now I want you to really notice and focus. You see how that standard deviation, when you put everybody's together, is much smaller than for any one person. Okay? So you can see that when Grace calculates the height, she says the trees are 1.6 plus or minus 0.2. Or Andy, he says 1.6 plus or minus 0.2 as well. But if I use all your data to make one average and one standard deviation, you see how mine is more accurate. I can say that the average is 1.6 plus or minus 0.07. So it's much, much more accurate. So the question is, if you're Grace, Sophie, Harry, Andy, or Amanda, you only have one set of data, right? You did it by yourself. So for example here, Amanda, she only has this data. So the question is, can she use her data to calculate this standard deviation here? And the answer is she can, roughly. And this is how you do it. Now I just want to give you some vocabulary. These are called, what did I say these are called? Standard deviations. But when you combine together, this is called standard error. So that's your first word today. Standard error. They're nearly the same thing. The only difference is standard error is when you're looking at the average of many averages, whereas standard deviation is for one data set. And they're nearly the same thing. They're nearly the same thing. What it is? Standard error is like the standard deviation, but for the mean average of the mean average.
Average value sigma.
Yes, it is. Yeah. It's like the average values sigma. Yes. Yeah. So it's nearly the same as standard deviation, except it's at a different level. It's like a level higher. Yeah, because each one of these is a mean average, isn't it? Of each person. And this is the average of these.
So the total mean average of the average.
Exactly. The standard deviation of that. Yes? Continue? Is your mind ready to continue?
Yeah.
You sure? Yes?
Go back
To what? To this?
my mind is gone.
Me too.
I think here.
I know, me too. Yeah, me too. Gone a long time ago. Okay, continue? Yes? So, I said there is a way actually to calculate this from this. So for example, like I said, if you're Amanda, you only have this data. So Amanda has no way of knowing what this is. It's impossible for her to know this, because she would need to know what the other people got. But in fact, there is a way for her to know this. And this is how you can do it. You can use this formula. That the standard error is roughly equal to the standard deviation divided by root n. Okay? Let me show you. If you look here. So here's Amanda's data. How much data does she have? How many points? 1, 2, 3, 4, 5. Yes? Here's her standard deviation. So I'll do standard deviation divided by square root 5. Now, in my example, the numbers are made up, so they don't match. That's why. But you can see it's not too different. 0.1 and 0.07. Now, no, I know the difference. They're different because I made up the numbers. My numbers are not following a bell curve. This is the reason.
values might be
Do you want me to?
more similar.
Yeah, actually, maybe I shouldn't have picked Amanda's. Maybe I should have picked someone else's. Let's see, who's the best?
Me.
No. Oh, yeah, okay, Hareen. Oh, right. Right, so we'll pretend we're Hareen now. Okay. Right. There we go. So you can see how his estimation of the standard error is quite close to the true value.
Yes.
So what this means for Hareen is his average is 1.73. So his average is 1.73. Is this the true average? No. It's his estimate. How far away is the true average? Well, what you're saying is the true average, it should be nearly this much away. Do you remember in physics we have this idea of uncertainty where the true value is between these two numbers? That's what the standard error is. It's the uncertainty for the average. So Hareen, he gets the average is 1.7. That's not really the average. The average is 1.7 plus or minus 0.07. So what we call standard error, in physics you call uncertainty. But there's just one small difference. There's usually a number here. So I'll write a box here. Now the reason for the number is because the standard error is 0.07. You would like to be right 95% of the time. So did Joan tell you why this number is important? No. Okay. So, you know?
95%.
Yeah, so did Joan tell you or did you know this?
But she said we learned this number.
Yes. If you go to your table book, you don't have to do it. No, you don't have to do it. You can trust me. If you go to the table book and look up the values, I think if you look up 0.975, you'll get 1.96 for 975. So that means here is 0.025. So if I go here to minus 1.96, how much is here? 0.025. So then how much is in here? 95%, 0.95, yeah. So this 1.96, if you go, yeah? This is 2.5%, this is 2.5%, the total is 100. Yeah? If you use 1.96 standard deviations, then how much area do you have? You have 95%. So if I go back here, if I use 1.96 standard errors, then I'll be right 95% of the time. In other words, if Hareen says where's it gone? Yeah, if Hareen says the true average is somewhere here, 95% of the time, he'll be right. 5% of the time, it'll be too far. So let's see what happens if we do it for him. The lower will be this number minus 1.96 times this. And the upper will be this number plus 1.96 times, let's try this again. No. Upper equals this plus 1.96 times this. So Hareen's saying in his research, the true average height of a tree is between 1.6 and 1.9. And can you see when we put them together, we got 1.6. So his bounds were accurate. Okay, so this should remind you a lot of what we do in physics. So we can put the formula together like this. Average minus 1.96 times standard deviation over square root n. And what do we call this part here? Standard error. 2 average plus 1.96 standard deviation over square root n. This is called a 95% confidence interval.
In our formula,
And this is in your formula book.
we don't have a 99% confidence interval, so we don't.
In the formula book there's only 95, so I think this is all they'll do for the exam. Now, this should remind you of what you did in physics. Do you remember in the lesson where you were calculating the residuals? Well, the residuals were a lot like the standard deviation. And you also remember the formula you divided by square root n. The only thing that's different is in physics I did not have this number. I just had 1 really. Yes, sorry.
What's the word after confidence?
Interval. Yeah? So what we'll do is we'll do one question and then we'll finish, okay? So have we got Joan's page there? Yeah, okay. So let's do the first question together. Can you read it out, Sophie, please? Wait, slow down there. Say it again, I can't hear you. Uh-huh.
Mean was 59 feet per minute, and the standard deviation 40.
Great. So we have this information. So 80 people were asked what's their beats per minute when they wake up, and the average was 69, and the standard deviation of the data was 4 beats per minute. Okay, so what's the first question then, Grace?
Find 95% confidence interval from
Okay, so this will be 69 plus or minus 1.96 sigma over root 80. Amanda, do you have a calculator? Or, yeah, Andy and Hareen, can you just give me the plus minus part? Is it raining? Yes. Hey, you're looking for Mark. Yeah, he's in 301. Yeah. 0.877. So what you're saying here when you have a result like this is that the true average is between whatever. I'm going to make this easier to do in my head. 0.88, is it?
Yes.
68.12 and 69.88 beats per minute. Okay. Amanda, what's the next part?
Should we write down the last sentence?
No. I'm just trying to explain what it means. Amanda?
All five samples would be need to, I don't know what to do.
Go on, try.
Estimate
Estimate, yeah.
Estimate the mean number of beats with 95% confidence to be plus or minus 1.5 beats.
Are you sure this was 0.88?
Pretty sure.
Yeah, no, I think it is. No, forget it. I believe you now. Right. So for the next part, they want to know how many people would you need so that you could be accurate to within, how much, 1.5?
Yeah, plus or minus.
Plus or minus. So for the next part, they want plus or minus 1.5. How many people would you need for that? So here it's 1.96 times 4 over square root n equals 1.5. Can you see you want the plus minus part to be 1.5?
Oh, it's positive?
No, it's a bit like you're saying you want the plus minus part to be plus minus 1.5. So I can just cancel this. By the way, this part has a special name. This is called the margin of error. Have you ever heard of that in English?
No.
No, okay. It means in English, how much of a mistake do you think you made? So, do you want this to be big or small? Small. How much would you like it to be? Yes. Right. So here we get n equals 1.5 over 1.96 times 4 squared? No, that's not right, sorry. 1.96 times 4 over 1.5 squared. What do you get?
Okay.
Yeah. 25?
27.
Point?
3. 32.
27 point.
32.
Right, so do we round up or do we round down?
Down.
No, up. Because the questions...
Oh, yes, I get it.
Yeah?
Yeah.
Okay.
Around 27.
Up to 28.
That person cannot be 27.36.
No, but why do you round up and not down?
Because if it's down, it's less than 1.5.
No, if it's down, it's more than 1.5. The question said you want to be at least this accurate. So if you make the n bigger, this is smaller, and smaller is good. If you make this smaller, 27, then this becomes bigger, and bigger is bad.
I thought you said.
You want this to be small.
Oh.
It's the x, huh? You have two choices. You can make n 27 or 28. You can't make it 27.3. If you make it smaller, this gets bigger. If you make it bigger, this gets smaller. Which is better, if it gets smaller or if it gets bigger?
Smaller.
Gets smaller. Like you said, you want it to be 0. Smaller is better. No, 28 is better. Because 28 makes this smaller. Oh my goodness.
Because n is in the
Denominator.
denominator.
Yeah. Yes? Yes. Oh, nice. Okay, is that the end of question 1?
Yeah.
Yes. Now, how many questions did Joan give you?
Everything.
How many? 10.
Only for this part?
For this part, that's all I care about right now.
3.
Oh my goodness, can you count, please?
There was a
For today? No. Oh yeah, okay. So today, yeah, okay. Huh?
10.
Ah, you gave me this question. That's fine. Yes. So these are all very easy then. Yeah, here is n, here's the average, here's the standard deviation, and here it is here. Yeah. Of course, I want you to finish this for our homework. All of them. Please. Because you did this with Yeah, but you did. No problem. We can do this we can practice these in revision. The business students also study this. So we can, I want to go home. Please, I know I want to go home. It's raining, but I still want to go home. The business students study this as well, okay? So we can do this and this in class, okay?
Yeah.
So can you try to finish what you did with Joan last time and do 5 of these for today? Okay? In the next math class, we will be all together again. I know that makes you happy. So, I will finish the trigonometry question and then I'll do some of the normal distribution. Maybe I will do exam questions, maybe I will do your worksheet. I don't know, I haven't decided yet. Okay, go away. I know you want to look at the labs. So, if you open it up, I can check it quickly before we go to the rain.
Sorry.
The rain!
Oh.